not intimidating. All right, just wait till you see me at the Seatbelt Fashion Show. You will feel far differently about me after that. You're gonna see, because I'm gonna change here when they call for the folks. I'm gonna go change in the stockroom.
Last year's pretty great.
Last year, Chewbacca. Yeah, that was pretty good. I still have the Chewbacca stuff back there. That'd be funny. All right, so here we go. I don't know what just happened there, but I said something I shouldn't have, and I put it, so I had to go back. So if you're listening to this and it sounds disjointed, well, the class reminded me I shouldn't use some language. There, so we'll send that out to the internet and see how it goes. Okay. So what we're going to talk about today are collisions. I want to preface, it didn't change. This problem is not. In this problem, there are two objects that are going to interact through a force. We call that a collision. A collision is anytime one object ends up being in contact with another object. That's a collision. And although you might not think of all things that we talk about as collisions, the moment the first object contacts the second, there's a force between the two objects. And although we know that the action of a force can be to change something's energy, during a collision, there's something more happening that isn't just about energy. You see, in a collision, the contact point, the moment in which object one contacts object two, there's no easy way to figure out how much energy is transferred from one object to the other. In fact, it probably is impossible to easily figure out how much energy is transferred from one object to the other. Part of the reason is because most objects that collide don't stay in contact very long. Collisions usually happen over a very short period of time, and therefore over a very small or completely insignificant displacement. So dealing with how you calculate work is nearly impossible. And although after the collision, each object might have an independent velocity, some of the energy might go into places that we are not prepared to deal with. Most collisions make noise. That's energy. Most of the collisions change the temperature of the objects that collide. That's energy. That energy all had to come from somewhere. It came from the collision. Most collisions don't conserve energy. More importantly, most collisions don't conserve kinetic energy or mechanical energy. Now, for the next few moments, I need you to hear this part very clearly. A collision, as we will define it, is the instant before two objects become in contact and the instant after two objects come in contact. A lot can take place before the collision and a lot can take place after the collision. But the collision itself is the instant before contact and the instant after contact. I won't draw it like that because I can't draw something like that. I can't draw the arrow. I can't draw them just that close together. So I will make it appear as though we're several seconds before the collision and several seconds after the collision. But that's not how we treat it. The collision happens almost instantaneously. And so we're dealing with the moments just before and the moments just after. And collisions, although are not about energy, are about a different measurement called momentum. Although mechanical energy is not conserved in most collisions, momentum always is. Now, as the topic goes, I want to really impress this upon you. Momentum is conserved in all collisions under all circumstances. There are no exceptions to this rule and no gotchas hanging out somewhere. Momentum always is conserved in all collisions. But again, I'm being very careful with my language because I'm talking about a collision as being defined as the instant before contact and the instant after contact. But there are no exceptions to this rule. There's nothing hanging out, in the future that's going to say, well, under this circumstance, that's not true. In all collisions, the momentum before collision is equal to the momentum after the collision. Now, a few words about momentum. If you don't have a definition or you weren't in physics before, then there are some things you should know. Momentum is inertia for objects that are moving. It's inertia for moving objects. You've probably heard the word momentum used in all sorts of capacities. Has anybody ever heard the phrase institutional momentum? We teach schools in this country in subdivided classrooms with about 30 kids per class. You get a 45-minute period and I tell you about something, or I make you work in small groups or do activities, and then the bell will ring and you will go to some other place and do something similar in somebody else's classroom about a completely different topic. This is probably not the best way to learn, but it's the method in which we are doing it in these schools. Changing that is very difficult to do because we have institutional momentum, meaning there are a lot of people invested in us doing it this way, and infrastructure has been created to do it this way. It would be difficult for us to change because we have institutional momentum. The word momentum here means difficult to change, in the same way that inertia means difficult to change. So an object with inertia is difficult to change its motion. That's what momentum is about. It's about inertia. Momentum is a measure of how difficult it will be to change the object's motion. It's more than just inertia. It's inertia through movement. That's why momentum is a measure of how difficult it is to change an object's motion while it's moving. A good example of that, and I hate using this example nowadays, but I still use it because it works. A bullet only weighs a couple of grams. If I have a whole bunch of them on the table, they are not dangerous sitting on the table. But I accelerate them through a gun, and they suddenly are incredibly dangerous. Their mass hasn't changed, but they are far more difficult to deal with while they've been shot than they are when they're just sitting on my desk. Giving something velocity makes the object more difficult to change. It's harder to change its motion. It has momentum. So inertia isn't enough. Momentum is a bigger picture of an object's total inertia. All right, the nitty-gritty stuff. We use lowercase p for momentum because, of course, that makes perfect sense. Out of letters. Got to go somewhere, right? Momentum is a vector quantity. And it is the product of mass and velocity. Mr. Shelton, this is like everything else. We're always multiplying those things together. 1/2 mv squared is mass times velocity. No. 1/2 mv squared is kinetic energy. It is a scalar quantity. The squaring of the velocity strips away any direction. And it is a quantity that can be increased and decreased, doesn't care about direction. Momentum is intimately tied with direction. It is a vector. And let me tell you, when it comes to measurements, we use momentum and the direction of momentum with far more care than anything else. The direction of momentum is incredibly important. In fact, momentum and energy are two sides of the same measurement. However, you need both of them to understand what's happening to an object. Energy carries with it something the object has, but momentum carries with it direction, and energy never can. So you need both. One of the most famous thoughts in all of science when it comes to physics is the Heisenberg uncertainty principle, which says that you can only know one thing about an object very well, but in knowing that one thing, you can't know other things very well. And it can be applied to momentum and energy. You can know the energy really, really well. The problem is that by knowing it really well, you don't know when it had that energy. And you can know the momentum really, really well, but in knowing it, you can't know where it had that momentum. Knowing one really well negates your ability to know the other. And kinetic and energy and momentum are intimate parts of how we understand the way the universe works.
Pardon the interruption. Please release those students that are participating and actually have a role in the pep rally. This is not to release everybody just yet. Please release band and winter sports to the gym right now. Please release band and winter sports. Thank you.
All right, so you guys always get screwed on these days. the unit for momentum is kilogram meter per second. That's, it has no special name. Although it's really actually, in many ways, incredibly important, maybe more important than force. We don't give it a special name. Kilogram meters per second are the units for momentum. And if we were to have some analogs between this and work and energy, with work, we said work would change something's energy. The analog is impulse, changes something's momentum. However, with work, any force can do work on an object. And so all forces acting on an object have the capacity to do work. Impulse is different. Impulse is defined. I use the word impulse, but your textbook uses a capital J. I never use a capital J for it. It's fallen out of favor. We don't usually use capital J for impulse for most things. We generally don't calculate impulse very often. So for you guys, I'll just write the word impulse out, but capital J is the letter. Impulse is defined as the way to change something's momentum. You apply an impulse to change something's momentum. But by definition, an object has to accelerate for its velocity to change. Therefore, an impulse can only be done by an unbalanced force. So there's only one way to calculate impulse and only one type of force to use, where all the forces can be said to be doing work on an object and they can be calculated individually. Impulse is the net force times time. These are all definitions. We're very unlikely to use impulse in calculation on the exam. We will use it quite a bit next semester, but very, very unlikely to use it now. Bite your head off, I promise. I want to talk about collisions. Collision problems are the most likely way in which you will have to deal with momentum on the AP exam, and definitely it's going to be on the semester exam. A collision is any time one object comes into contact with another. In a collision question, we are generally tasked with figuring out the results of the collision. There are three kinds of collisions. Three kinds. And we're probably only ever going to see two of them. Kind number one. In kind number one, the two objects stick together due to the collision. So, got a 5 kilogram object traveling at 2 meters per second, strikes and sticks to a 10 kilogram object during the course of their collision, basically becoming one object of mass 15 kilograms. I'd like you to be tasked with finding how fast the two objects move after the collision. This is hands down the most common example of what you'll have to do on the test. And it has a name. It's called a perfectly inelastic collision. Kind of a stupid name, to be honest with you. What's so perfect about it? This one loses the most energy in the collision. I'm not sure what is perfect about it. It doesn't matter. That's what we call it, a perfectly inelastic collision. In any collision, the momentum before the collision is equal to the momentum after the collision. So in a collision problem, the first thing you should do after identifying where the collision takes place is identify a common direction that you will call positive both before and after the collision. Deal with direction and deal with it clear. Now, you need to add up the momentum of each object before the collision and set it equal to the momentum of each object after the collision. I have two objects before the collision. 5 kilograms times 2 meters per second plus 10 kilograms times 0. After the collision, I really have one object of mass 15 kilograms, but I don't know how fast it's traveling after the collision. This is generally how these problems work out. Now, clearly I have 10 kilograms meters per second of momentum before the collision, so I must have the same amount of momentum after the collision. So, under this circumstance, I can tell you what the velocity must be. The only way to ensure that the momentum remained constant is to recognize that the velocity afterwards has to keep the momentum the same. Yeah? It's 2/3. Thank you. That would be best if I continue to do mathematics good. I'd be gooder at mathematics today. Basic, simple, straightforward. Any questions about this? All right, well, the obvious next step is to consider a collision in which it's not perfectly inelastic. Now, what that means is the objects don't stick together. Now, to be fair here, in this circumstance, you're going to be disappointed. I'm going to label this V5 and this V10 so I can differentiate them. I didn't change anything about the before case, and you'll notice I'm not moving the other box. I could do all those things. But in this circumstance, I have 5 times the velocity of the 5 kilogram box plus 10 times the velocity of the 10 kilogram box. Now, that's it. That's as far as we can go. If all I had was the velocity of the first box, in most collisions, the result is unknown. You see, the thing about most collisions is that if the objects don't stick together, we don't know how the energy got distributed. If one of the objects had a really rigid outer coating and the other one was kind of soft, well, the way in which they interact is not obvious. And because of that, we don't really know how much of the momentum is transferred. It has to do with how long they actually stick together. That's what will determine how much of the momentum is transferred from one object to the next. But it also is based on how much normal force there is between the two objects, and that can change depending on how soft one object is compared to the other. So what happens here is I have two unknowns afterwards to which I don't have an answer. So I would have to be given one of these velocities if I wanted to figure out the other. So in an inelastic collision, that's often not given on a test, unless there's some other thing given. Like, what if they tell you that this whole thing took place on a table? And because it took place on a table, one of the boxes made it to the edge of the table and fell off and landed this far away from the table. Aha! Well, they've given me extra information, right? They've told me where one of them fall. I'm being sent a message. Mr. Shelton, your...
Caller?
I just want to get to a conclusion. Let me get close to it. So you see this, right? You see the two-part problem here? You know, I tell you it lands, 2 meters away from the edge of the table. I tell you how tall the table is. You could figure out then how fast this block was going. And because of that, you can figure out the other one. That's the kind of AP stuff we're going to see. That way they can work in a projectile problem and a collision problem all at the same time. Now, I wouldn't do that. This is on the exam for sure, but in the unit we're on now, probably more likely, this box is connected to a string and it swings upwards. Because this, well, no, look, not more work, different work. This is conservation of energy. If I want to make a problem that involved momentum that was still related to what we're studying right now, I wouldn't go all the way back to projectiles. I'd do this problem. Because this box gained potential energy after the collision. I could figure out how much kinetic energy it had after the collision and use that to figure out how fast the other block was traveling. This is the kind of stuff that's going to be on the exam. The collision will be in the middle somewhere, but there'll be some kind of conservation of energy or a projectile or something that will happen before or after, whose consequence will help determine what happened during the collision. Yes, sir?
So we would be told the height that.
By reminding you of some of the situations that we have seen recently. Here's a simple situation, and as you look at this situation, I want you to think about the snapshots I'm purposefully including here. There it goes, okay. Can you imagine this scenario? Right, I put the ball at the top of the little ramp, the ball rolls down the ramp. Imagine I'm just looking at this and I take 4 pictures. This represents 4 instances in time. In none of these instances is the object staying there for very long, right? Even though it might be stopped at the beginning and stopped at the end, it doesn't stay stopped. If there was nothing to take the energy out of this system, this object would likely go back and forth in perpetuity, right? Forever. Can you guys imagine that? It starts with some gravitational potential energy. It starts to convert that to kinetic energy, converts it to even more kinetic energy as it gets closer to the bottom, and then strikes the spring, converting that kinetic energy into elastic potential energy until the object stops. And then, of course, after it stops, the spring pushes the ball back out, and the whole process starts over again. That energy stays here in the system. And although 2 forms of this energy are potential, which requires the interaction between the object and either the earth or the object in the spring, in this system, we generally are talking about the energy as it pertains to the ball. Does that make sense? We're talking about what's happening to the ball. Energy problems generally, and I say this generally, energy problems generally are about a single object and what happens to it. They're easy to identify. Look for the interaction of the object with the spring. That's a dead giveaway that you're likely going to use energy. Look at the object changing its height. And especially look for situations in which the path that the object takes is not uniform. Circular paths, curved paths, paths in which perhaps you can't predict what the shape looks like easily. Under those circumstances, all you've really got is to take a look at the different states and hope that energy is being conserved. I say hope because energy will be conserved unless there's an external force to take that energy away. Now, this problem is a clear energy problem. I see all those things in it.